All right, this video we're going to explore the Poisson distribution. This is one of our discrete distributions, and so we say our random variable x has a Poisson distribution with parameter lambda t, and is given PDF, so its probability distribution function, or its PDF. Here it's written as p. We were often using f of x, so f of x is equal to e to the negative lambda t to the x, all over x factorial. Right? So in the discrete case, remember, if I want to find the probability x equals, we'll say a. That is our PDF in the discrete case, right? So that is equal to our f of a, or e to the negative lambda t to the a, all over a factorial. All right, so that is just a PDF for the Poisson distribution. And so it is very much like the binomial distribution, where n is very large and p is very small. All right, so common examples of that are the number of accidents at an intersection, we'll say. This is a common example. Typos on a page. On a page. So you'll look at certain examples. Probably it'll say in the problem that it is a Poisson distribution, so it will be easy to identify. One thing to note is our lambda there. So the lambda is the average number of outcomes per our unit, and it could be a unit of time, distance, area, volume, but it's per one unit. All right, so let's look at an example over here in action. I'm going to skip all the way over to this one. Okay, so here, changes in airport procedures require considerable planning. Arrival rates of aircraft are important factors that must be taken into account. Suppose small aircraft arrive at a certain airport according to a Poisson process at the rate of 6 per hour. All right, so right there, that's telling you lambda is 6, and your unit of time is hour. All right? So we could say that, so t is, we'll say, in this, well, we don't know yet how many hours. So our unit is hours. All right. Thus, the Poisson parameter for arrivals over a period of hours, so however many hours, is 6t. All right. That is, x is a Poisson distribution, lambda t, so it would be 6t. All right. So that's what we know. All right. So now let's come down here. A. What is the probability that exactly 4, so if I were to write A down here, the probability exactly 4, so we know that's equals to 4, craft arrived during a 1 hour period. All right, so that is, in this case, t is equal to 1, right? We're not doing it over more than 1 hour. All right, so we could say that, in this case, x is Poisson distributed just with lambda t is really just 6. Okay? So we know by the formula that's on that previous page, it's equal to e to the negative lambda t, so negative 6 lambda t, so 6 raised to the k, so raised to the 4th, all over 4 factorial. It's easy to solve. That's our answer, whatever that approximates to. All right, let's look at part B. What is the probability that at least 4 arrive? Well, we know that is x is, so it's got to be 4 or more, so x is greater than or equal to 4, or 1 minus the probability x is less than or equal to 3. You can actually count them up by summing up several of the ones above, or you can use a Poisson table, which in the back of the book there is one. or else you would just write it out as 1 minus, so that's 0, 1, 2, or 3, or I could write a sum, right? So k equals 0 up to 3, e to the negative 6, 6 raised to the k all over k factorial. So that's how you would calculate x is greater than or equal to 4. Okay, so C is the one that shows us a little bit about the power of lambda t, or how that t actually comes into play. If we define a working day as 12 hours, what is the probability that at least 75 small aircrafts arrive during a workday? So this is a slightly different one. So above, t was equal to 1. Here now we have t is equal to 12. So I could then define this new random variable y, which is Poisson, and this time 6 times 12, right? Or what is that? 72? So y is a Poisson random variable whose parameter is 72. And what were we looking for? That at least 75. So we have the probability that y is greater than or equal to 75, right? And that goes on for infinity. So this is 1 minus the probability y is less than or equal to 74, right? We can do this since it's discrete. We can use the chart because that's a lot of ones to sum. But if I were to write it in summation notation, it's 1 minus the sum of k equals 0 up to 74, e to the what? Negative lambda t, so to the negative 72, 72 to the k all over k factorial. All right? That's how we find our probabilities using the Poisson distribution.